Okay, welcome back, everybody. Ended yesterday's lecture with a discussion of generating functions. Here was our definition. So, given a sequence, a sub k, its generating function uh, is this series, which, as we noted, if give me 1 second. As my cats are fussing at me for food. So I have to appease them or they're gonna drive me crazy all lecture. So give me 1 second and I will continue. Um, okay. Given a sequence a sub k, k bigger than or equals 0, its generating function is defined to be this series. We noted that if you're talking about a finite sequence, it's just a polynomial. If you're talking about an infinite sequence, and this is a power series, having that sequence as its coefficients. Okay. This couple of the examples that we gave, like if, for instance, we knew specifically that here's our sequence, just minus 1 to the k over k factorial, then the matching power series is just the power series for e to the minus x. We first saw this in the example we did right before, where I was asking specifically about the probability of a given configuration of shuffling student quizzes being a derangement. And we saw, of course, that there was this power series for the exponential function showing up in this example. So here, just giving another example of this being the Maclaurin series. Remember, Maclaurin series is just a Taylor series for a function expanded about 0. So this is the Maclaurin series of e to the minus x is going to be the generating function in this case, because that is exactly the power series that we get. If we chose this a sub k to be in choose k, then the resulting generating function is 1 plus x to the n by the binomial theorem, right? Because by binomial theorem, this expression is exactly this generating function, which is 1 plus x to the n. Okay. Now, of course, the question that I asked at the end of yesterday's lecture was, how can I actually use this to solve combinatorial problems? And I promised that we'd do this next time. So next time is now. How do I use generating functions to solve a combinatorial problem? So the first example, and this is maybe call this like the canonical example of how to use generating functions to count it truly is the canonical example because it is even sort of the thing that kick-started the whole field of combinatorics, and where you see appearances of like Pascal's triangle and these binomial coefficients showing up for the first time. Okay. So, what is this particular example? This is the following. Um, so, we have done this problem in another way, but we're going to do it in a different way now. So let's say that we are determining the number of k element subsets of an n element set, right? So determine the number of k element subsets of an n element set. We know what the answer is already, right? So we actually know that, so we fix n let a sub k denote this number. Of course, we already know that this number is exactly, well, if you want to write it, this is n choose k, or sorry, n choose k. This is n to the k falling over k factorial. Okay, for instance. But we can figure this out in another way, right? So, of course, we counted this in one particular way when we first introduced it. But the question is, well, what do we do if we're not using what we did before? What do we do, and how do we use generating functions to do this? So, if I'm going to enumerate all these subsets, if I'm going to construct a single one of these, how does that work, right? So construct a k element, we'll say. But how do I do this? Well, let's say that I'm picking which elements I'm going to put in the subset and which I'm not going to put in. So, so we are choosing which elements to include and which to exclude. I'm not making a reference to inclusion exclusion here. Okay. So we're choosing which elements to include, which to exclude. If we're going to include an element, then we are going to say that this is our, we'll denote this by x to the first. And if we're going to exclude an element, we'll denote this by x to the 0. Right, the 1 and the exponent here for include, the 0 for omit or exclude. Seems natural. We'll use the plus symbol to be or. So then in this way, to include or to exclude would be written. Why did I write it as a subscript? So if I wrote this as x to the 0 plus x to the first, this is the choice of whether to include or exclude, right? A single element, right? That is what this expression means. We will use multiplication to denote and. So if we're thinking of like the logical and, using multiplication for this, thus how to make n choices to construct a subset, because we have an n element set. We have to decide whether we're including or excluding each of the n elements. So to include or exclude a single element is this expression, x to the 0 plus x to the first. So then multiplying, right, x naught plus x to the first times x naught plus x to the first. This would be whether to include or exclude this element, whether to include or exclude another element, right? And so if we continue on here, where I have n copies, this expression is telling me what? This is the n choices to be made, right? So this is modeling, and maybe I'm not saying I'm pointing to any particular thing here, I'm pointing to the whole product. So this models the n choices that I have to make here, right? All right. So models the choices required to form such a subset. Okay. So, of course, we can expand this further, right? So, knowing that this binomial thing, of course, now you see its relation to the binomial theorem. This binomial expression here, I could expand this, and this is going to make sense both arithmetically, like in terms of the arithmetic I've written down here, and logically, because we can distribute and across or in the exact same way that the multiplication distributes across the addition sign, and you can do this because that's how these operations work, right? View these as sets, right? Now you go to, say, set intersection and set union, right? And look at how those set rules work, and distributes across or in the same way. Okay. And so, for instance, right, like in the n equals 3 case, what does this look like? This would be x to the 0 plus x to the 1 cubed. And if I were to expand this out by just multiplying that binomial by itself, 3 copies of itself, what am I going to get here? I get the term with all of the exponents being 0 multiplied together, plus these two being 0 and this one being 1, plus 0, 1, 0, plus x to the 0, then x to the first, plus x to the first, x to the 0, x to the 0, plus x to the first, x to the 0, x to the first, plus x to the first, x to the first, x to the 0, plus term with x to the first, okay, for each copy of x here. So, what is this? This term is where I have excluded all elements, right? So for n equals 3, this is a 3-element set. This is giving me, I have excluded all of the elements, right? So I haven't picked a single element, so the resulting subset would be the empty set. Here, I've excluded the first 2 elements and included the third. Here, I've excluded the first and third element and included the second. Here, I've excluded the first element, included the second and third. Here, I've included the first and excluded the second and third, and so on. Okay. Now, of course, x to the 0, that's just 1. X to the 1 is just x. So we could rewrite this expression using our, normal algebra sense. So this is 1 plus x cubed, which of course is 1 plus 3x plus 3x squared plus x cubed. And we note that the coefficient of the x to the k term in this expression is telling me what? It is the number of subsets of a 3-element set having exactly k items. Having exactly k elements. So there is one subset of a 3-element set that has exactly 0 elements. There are 3 subsets of a 3-element set having exactly 1 element. There are 3 subsets of a 3-element set having exactly 2 elements, right, determined by which thing you're excluding. And there's exactly 1 subset of a 3-element set having exactly 3 elements. That's the whole set itself. So these coefficients are exactly counting the thing that you're wanting there. You, of course, know that these coefficients are the binomial coefficients are these n choose k. And so by the binomial theorem, the generating function g of x in our case yields, so our generating function is 1 plus x to the n. This yields that a sub k is exactly the coefficients in the binomial theorem. So it's n choose k, or n to the k falling over k factorial. So these coefficients have to match up, and that is exactly what this says. You can view this in another way. So we computed the binomial coefficient things first, right? From a count, we counted what this thing was, we wrote out what it was, and then we did the binomial theorem. But if you actually look at the binomial theorem proof that we did, the binomial theorem proof relied purely on like the algebra and like the arithmetic of how we define the things. We did it by induction. It didn't rely on anything. It just relied on some very basic identities and reindexing. So in a way, this is an alternative proof. It's not a circular proof of that count that we originally did. We could have actually used the binomial theorem and generating functions in this way to show this. This could have been done originally using this exact same thing. And in fact, this was the way that this was sort of approached when mathematicians had access to this. If you go back and look at a lot of the early work, it's mostly Pascal, maybe Fermat. There's a few other early mathematicians, early like 17th century mathematicians that did a lot of work with this stuff. So anyway, this is the reason I called this the canonical example of how to use the generating functions to count. Is like this is essentially showing you what it is that is going on here. So the question of how to use generating functions. So how to use generating functions is two main steps here. So first, express problem in terms of determining one or more values of an unknown sequence. We'll call the sequence A sub k. And two, determine a generating function for this sequence. Writing x to the k as representing selecting an object k times then using addition to represent alternative choices this is the or bit, and multiplication to represent sequential choices. So I'm going to underline a few of these things here. So determine a generating function. The x to the k term in the generating function is representing selecting an object k times. Addition represents alternative choices that can be made at each step, and multiplication represents sequential choices. Go back and look at the example we just did with the binomial theorem and repeating this count of the number of k element subsets of an n element set. Go back and look at that to see, oh, yeah, this is just exactly what we did. Okay. Now, at the end of this, you could say, well, how did this, at this step, am I done? Like, what have I done here? I wanted to find the terms in this sequence. So, determining generating function, how does that help me? There is third and final step, which is using analytic or algebraic methods to expand the generating function and determine the values of the sequence. So use analytic here. This could just mean doing the algebra of expanding the thing. So use analytic methods to expand the generating function g of x and determine sequence values. Determine values of the sequence a sub k. Okay. So this is how this goes. Let's do one example before I go on to my specific examples here. So here's example. In this example, we'll say that we have a drawer that contains 12 beads. The 12 beads in a drawer, there are 3 red, 4 blue, and 5 green. Okay, 3 red, 4 blue, 5 green. Now, I want to know the number of ways to select 6 beads from this drawer. Okay, if beads of the same color are indistinguishable and the order of selection is irrelevant. So beads of same color are identical. Order is irrelevant. That's important because these are not like marked beads, like they're not labeled. There's not like red 1, red 2, red 3, green 1, green 2, green 3, and so on. So this matters. The beads of same color can't be distinguished, and the order is irrelevant. Okay, so those things being equal, what's the number of ways to select 6 beads from a drawer? Let a sub k be number of ways to select k beads from the drawer. Okay. How can I come up with a generating function for this? Then the generating function gx for the sequence is g of x. So just going back to the previous page here, I was presented with a problem about counting the number of ways to select 6 beads, okay, from a drawer in this context. In order to use a generating function to answer this, I need to express the problem in terms of determining one or more values from an unknown sequence a sub k. So I did that by letting my a sub k term be the number of ways to select k beads from a drawer. So if I'm interested in the number of ways to select 6 beads from a drawer, a sub 6 is what I'm looking at here. Right, a sub 6 is what I'm interested in, but I rewrote this more generally as a sub k is the number of ways to select k beads from a drawer. You'll see why I did that in a second. Okay, all right, now I've been asked to determine a generating function, or I haven't been asked, this is just what I'm doing to solve the problem. Determine a generating function for the sequence using x to the k as representing selecting an object k times, using addition of these different monomials to represent alternative choices, and multiplication of these monomials is representing sequential choices. And then using analytic methods to expand this generating function, deal with it, simplify it, however, in whatever form I can use it best, determine values of this sequence. Okay, so what is this? How do I view this? How do I construct this generating sequence? So, selecting beads from a drawer. I can select how many red beads. I can either select 0, 1, 2, or 3. Okay, so whatever selection has been done, I either select 0, 1, 2, or 3. If I'm using x to the k to denote selecting something k times, selecting a bead k times, then x to the 0 red beads, that's 1, right? This is my x to the 0 term. Or I could select 1 red bead, or I can select 2 red beads, or I can select 3 red beads. But that's it. Beads. Next in the sequence, now there's sequential choice happening, so this is a multiplication, is the number of blue beads that I'm selecting. Again, I can select 0, that's x to the 0, or I'm just going to go ahead and shortcut this and write 1 here. Or I can select 1 blue bead, or I can select 2 blue beads, or 3 blue beads, or 4 blue beads. And once I'm done, that is the number of blue beads I've selected. Then I have green beads to select. This is next in the sequence. I'm going to write this as multiplication, but then I'm going to actually write it down here so that I have more room. So this is 1 plus x to the first plus x squared plus x cubed plus x to the fourth plus x to the fifth. And that is it. That is my last thing. Now, I can do this by hand. It's pretty annoying, but I could do this. right? Let's say that I've already done this, and so the resulting expanded thing is 1 plus 3x plus 6x squared plus 10x cubed plus 14x to the fourth plus 17x to the fifth plus 18x to the sixth plus 17x to the seventh plus 14x to the eighth plus 10x to the ninth plus 6x to the 10th plus 3x to the 11th plus x to the 12th. Where is the solution to our question in here? Well, what we saw was the number of ways to select 6 beads from the drawer, but that's a sub 6. We found the sequence a sub k for selecting k beads from drawer. What is a sub 6? A sub 6 is the coefficient on the x sub 6 term. So a sub 6 is 18. So 18 ways to do this. So under those conditions, there are 18 ways to select 6 beads from the drawer in this. If you want to see this verified, there. There's all 18 such ways. Okay. You see how this could potentially be used in situations that might otherwise be kind of hard to come up with how you would perform a count of some of the objects. The power here is in like how simple the actual like underlying thing you're doing here is, right? You're basically all you're doing is relying on this setup, this nice analogy between addition and multiplication, and writing your the number of ways to select k things as it's the coefficient on the x of the k term. So x to the k is denoting making a choice k times of whatever object it is you're talking about. And past that, it's some algebra and maybe some analysis, right? Maybe you get an expression where taking derivatives to simplify things makes sense. We'll do examples of that. And so you might be able to see the beginnings of how powerful this approach is, and we're going to see many, many applications of this. This is just the beginning. So on to the many, many applications of generating functions. So basically the rest of lecture today, and maybe even some going into tomorrow, is going to be just different ways you can use generating functions. So here's one, double decks. So question, how many 5-card poker hands can be dealt from a double deck? How many 5-card poker hands can be dealt from a double deck? So what does this mean, double deck? So let's say you have 2 identical decks. So you can't tell the difference between, say, the ace of spades from deck 1 and the ace of spades from deck 2. So when you are dealt a hand, this is like dealing a hand from a standard deck, except now in your hand, each card that you get could be selected twice. So you can get the ace of spades twice. You can get the 10 of hearts twice in your hand, right? So there's a related, more general question. How many ways are there to select m items from n different items where each item can be selected at most twice? How many ways are there to select m items from n items? We'll say, uh, you know, these are n distinct items where each item can be selected at most twice. Well, whatever this number is, how many ways there are to select m items from n distinct items where each item can be selected at most twice. Let's call that by a double indexed sequence T n m, where n is fixed and m is some non-negative integer. Let g of x be the generating function for this sequence T n m. Okay. Again, this is why it's important. N's fixed here, so m is these are indexed by m, if you like. Okay, so that you don't have to struggle too much with this double indexing because the n is fixed. So, if this is the case, what is g of x? Maybe g of x isn't as complicated as you think, right? Because in selecting an item, right, in selecting an item, what can I do, right? If I'm have m items to select here, each object, right, each of these items can be selected at most twice. So that means my choices for the number of times I can select a particular item is either 0 times, 1 time, or twice. Right? Those are the options. And so those are my options for selecting an item. There are n distinct items, and so this is my generating function. And again, this is because every item, there are n of such items, can be selected either 0 times, 1 time, or twice. So, how do I find a value of this sequence? Well, I have the generating function for it. So in order to do this, I find the coefficient of the x to the m term in this generating function. So I need to expand this. How do I expand this? Well, I noticed that this is a bino this is a binomial. Okay. In fact, you might look at this and say, wait a second. I could do this with any multinomial, right? I could view it as a binomial at each step and proceed in that fashion. Yes, in fact, you can do that. But that's what we're going to do here. We're going to use the binomial theorem twice. So I'm looking for the coefficient on the x of the m term here to answer this question. So let's write my generating function. This is 1 plus x squared to the n. Again, noticing that I could view this as a binomial. 1 is one of the terms and x plus x squared is the other. I can use the binomial theorem. So this would be the sum over k of n choose k times 1 to the n minus k, which is just 1. I'm not even going to write that here, times x plus x squared to the k. Okay. Now I can pull, there's a common factor of x here that I'm going to rewrite and pull out here for a second. So this is sum over k of n choose k times x to the k times 1 plus x to the k. But then this 1 plus x to the k, I can use the binomial theorem on that. So using the binomial theorem on that, I'm going to use a different index here because, of course, this is binomial theorem for a fixed exponent k, so I'm not going to use k as the index for the binomial theorem here because that wouldn't make any sense. So this is the sum over k of n choose k times x to the k. Using the binomial theorem for this would be the sum over, say, j of k choose j. 1 to the k minus j is 1. X to the j is the other expression. Doing some algebra here and rewriting this, simplifying this. This is the sum over k, the sum over j of n choose k times k choose j times x to the k plus j or j plus k. But now I can reindex here. I've mixed my indices here, and I can swap. I can reindex here by replacing every instance of j plus k with m, and I can make this a sum over m instead. So substituting m for j plus k, what do I get? I get the sum over m of sum over j of n choose m minus j times m minus j choose j times x to the m. This is substituting m for k plus j. Now, what is it that we were doing? Well, of course, we were trying to identify this coefficient on the x to the m term here, which we just did. So this means this number we sought, which was the number of ways to select m items from n distinct items where each item can be selected at most twice. This is exactly this sum. How does this sum go? This is a sum from j equals 0 to the floor of m over 2 of these coefficients n, choose m minus j, times m minus j, choose j. Why is this the last non-zero term? You can think about that for a second. If you're uncomfortable going ahead and writing this to show exactly where this ends, there's nothing stopping you from just writing it as the sum over j. Compute a few values of this and you'll see where this stops. Okay. So then my original question was, how many 5-card poker hands can be dealt from a double deck? Of course, now I'm prepared to answer a more general thing, but this was my original thing that I was interested in. So how many 5-card poker hands can be dealt from a double deck? The answer is, according to this, 5-card poker hand here would be this would be t sub 52 5, right? And so what is this? This is going to be 52, choose 5 minus 0, times 5 minus 0, choose 0, plus the next term in the sum is 52, choose 5 minus 1, so 52, choose 4, times 5 minus 1, so that's 4, choose 1, plus 52, choose 3, so this would be 5 minus 2, times 5 minus 2, which is 3, choose 2. You can tell that this is going to be the last term because in the next expression, I would have, like, if I was continuing this, right, this would be like 52, choose 2, and then 2, choose some number larger than 2, so you'd get a 0 there for that binomial coefficient. So this is, in fact, the last term. Doing this is how you see that this is what's happening. Okay, so j equals 2 is the last term. You have the j equals 0 term, the j equals 1 term, and the j equals 2 term, right? Okay, now in total, this is, if you actually compute this, this is 3,748,160. But you might have noticed that the form that this takes we have another way of explaining this, right? In fact, you could have come up with this on your own in using other reasoning, not using generating function, although essentially what you're doing is equivalent to what's going on here. Where does this expression come from? Like, apart from this generating function business, what's a way of thinking about this? Well, this is like me talking about how many cards have been repeated, right? So there's 52 choose 5 times 5 choose 0. That's just 52 choose 5. Ways of dealing a 5-card poker hand where none of the cards are repeated. And then there's 52 choose 4 times 4 choose 1, ways of dealing a 5-card poker hand where one card is repeated. And then there's 52 choose 3 times 3 choose 2, ways of dealing a 5-card poker hand where 2 cards are repeated. 3 cards being repeated isn't possible in a 5-card poker hand because that would need a minimum of 6 cards. So that is the reason why this doesn't continue. That is the reason why this is the last term, because you can't have 3 cards repeated. So you could have mimicked this entire thing in a very quick fashion by carefully counting how many ways there are to deal these poker hands, by separating it out into how many cards are being repeated. So the first term is 0 cards repeated, the second term is 1 card repeated, and the third term is 2 cards repeated. That is a completely fine alternative way of computing this. Okay. All right. More like this. Let's do more. So another example. Let's do counting with repetition. So what do I mean here? So suppose there is an infinite, oh man, that doesn't sound good for counting, right? Supply of each of n distinct objects. Okay. How many ways are there to select m objects from these n objects if I can select an object as many times as I want? So now you see what we're getting at here. So imagine you have an inexhaustible supply of n types of objects, right? It could be n action figures from your favorite series, right? Whatever you're into. Infinite number, inexhaustible supply of Godzilla figures of each type. Right, so you've got all kinds of different types of Godzilla. We'll say n distinct types here. How many ways are there to select m objects from these if I can select an object as many times as I want? So I could just select the same object over and over and over again, right? Maybe I really love a particular character and I just want to fill my house with figures of that particular character over and over and over again. However, this is, let's let a sub nm denote this number. So this, when I say this number, this is the number of ways to select m objects from these n objects if I can select an object any number of times I want to. Okay. Then, for fixed n and m greater than or equal to 0, the generating function of this sequence is what? I can select an object as many times as I want to. There's an infinite supply here. And so this is me selecting the object no times, 1 time, 2 times, 3 times, and so on. It doesn't stop there. And that is raised to the n because in sequence I'm thinking of selecting each of the n types of object in this way. So the thing is that what I have written here, however, can be thought of formally, right? worried about questions of convergence here, even though they do come up sometimes, but we're treating these formally. Here, this is really just the geometric series. And we know that because this is a geometric series, if the absolute value of x is smaller than 1, there is a very nice, very simple closed form expression that just allows you to evaluate that series, right? Geometric series is one of the few series. Geometric and telescoping are basically the only two series we can just compute. There's like a couple other mixed like examples, but for the most part, computing the actual sum of a series, even if you know it converges, is just impossibly difficult. Just very, very hard. So if it's not geometric, not telescoping, you're kind of out of luck in most cases. Here it is geometric though, so we actually know how to deal with it. And again, you might say, but how do I know that the absolute value of x is less than 1? We are using this as like an abstract object here. We're not concerned with these particular values of x at the moment. We're treating this purely formally. There are contexts where this you might have concerns here and you might want to be more careful, but for now we don't care about that. This can be rewritten as 1 over 1 minus x, that's the inside part, to the n. Okay, so of course this converges if absolute value of x is less than 1. We ignore this for now. Okay. And so, whatever this is the coefficient of x to the m, right? If we call this g sub n here, since technically this generating function depends on n as well, but n is fixed here, this is the coefficient of the x to the m term in this generating function. Okay, so this is what we're looking for to answer this question that we had up here. All right, but first, let's do something else. So first, we consider a more general thing. So let f of x be the expression 1 plus x to the alpha, where alpha is a real number. So this alpha is just some real number, i.e., it could be 0, it could be negative, and it could be irrational, right? It might not be a rational number. In particular, it might not be an integer, either a positive or a negative integer. It might not be either of those. Okay. All right. Now, we could compute a few things. So f prime of 0, this is its derivative, is just alpha. F double prime of 0 is alpha times alpha minus 1. And in general, the kth derivative of f evaluated at 0 is alpha to the k falling. You had to do these sorts of computations, right, in Calc 2 and in other contexts where, so Stat 410, if you did moment generating functions, you say, hey, wait a minute, you know, moment generating functions, and all these are related to, all these are related to power series, right, or just our power series. What is the thing I'm computing here? I'm computing the coefficients in a Maclaurin series for f, that is a Taylor series expanded about 0. And so the Maclaurin series of f of x is f of x, that is 1 plus x to the alpha. This is the sum over k non-negative of alpha to the k falling over k factorial x to the k. Now, you look at this and you immediately say, wait a minute, why can't I use the binomial coefficient here to write this down? And then I have to remind you, well, because alpha is a real number. So what binomial coefficient are you going to use? Alpha choose k? What does it mean to select k objects from, 3.1415926, pi objects, right? We don't have a notion for that, but this does suggest, or rather motivate, a definition of exactly this. So this expression, of course, we obviously recognize as playing the analogous role to n choose k in the normal binomial theorem, and so this motivates the following definition: to just take these coefficients and define those to be the generalized binomial coefficients. So the generalized binomial coefficient is alpha choose k, where alpha is a real number. This is exactly this expression, alpha to the k falling over k factorial, if k is non-negative, and 0 if k is negative. So here k is just an integer. Alpha is a real number. We can define the generalized binomial coefficient in this manner, which, if we believe in convergence of these things, we have the following theorem. Of course, note, first of all, alpha is a positive integer, then this is just the usual binomial coefficient. Right? So this works in exactly the same way if alpha is a positive integer. Otherwise, it's defined in this way. We have the following theorem, which says if absolute value of x is less than 1, or alpha is a non-negative integer, then 1 plus x to the alpha is the sum over k of alpha choose k, x to the k. This is the generalized binomial theorem. And its proof I'm not going to do. We'll say this is a result of Bernstein's theorem concerning convergence of Taylor series. It's not done in our textbook. This is done in many real analysis textbooks, so lots of different places that you can look this up if you're so inclined. But we're still not ready. So first, one more identity before we answer our question. So one more identity before answering our question. This is known as negating the upper index. So, alpha is a real number and k is an integer. Then this generalized binomial coefficient is equal to minus 1 to the k times k minus alpha minus 1. Choose k. Think about why this is called negating the upper index. All right. So, quick proof. If k is negative, this is obvious because they're both 0. So both sides are 0, right? We defined this generalized binomial coefficient to be 0 if k was negative. So if k is negative, then both of these are 0, and this is true. So assume k is a non-negative integer. Okay. Then we have the following. So choose k, is can be written as 1 over k factorial times the product from I equals 0 to k minus 1 of alpha minus I. That is just another way of writing alpha to the k falling. Reindexing this product, replacing each I by, so replace I with k minus 1 minus I. And in this way, we get that this is 1 over k factorial times product from I equals 0, k minus 1 of alpha minus k minus I minus 1. I could flip each of the k terms in this product. Doing that is multiplying by minus 1 in each of these k terms. There's k terms, so this would be minus 1 to the k. So this would be minus 1 to the k over k factorial times the product of these things flipped in each term. So this would be k minus I minus 1 minus alpha in each of these. But then this is just exactly minus 1 to the k times k minus alpha minus 1. Choose k. Which is exactly what I wanted to prove. So I have this property. Okay. Now, how do I use all these facts, to solve my original question? So what is my original question? Let's go back. Original question. How many ways are there to select m objects from these infinite supply types of objects? If I can select an object as many times as I want, we found here's the generating function. There it is. Solving this completely is computing the coefficient of the x to the m term in this generating function. Okay, so this does it. This is what I was looking to do. Exactly this. All right. So my generating function is 1 over 1 minus x to the n, or rewriting this, 1 minus x to the minus n. Oh. All of this was just to use the generalized binomial theorem, right? We needed the generalized binomial theorem because this exponent now is going to be something other than just a positive integer, right? Okay, so there it is. Using this generalized binomial theorem, remember, here it is. I get that this is equal to the sum over m of minus n, choose m, times minus x to the m. It's because this is minus x, right? The statement of the binomial theorem has it as 1 plus x, so this 1 minus x would be rewritten as 1 plus minus x to make this work in the general binomial theorem. Okay. Now, using this negating of the upper index here, this is equal to the sum over m of n plus m minus 1, choose m, times x to the m. And so, a sub nm is the coefficient on the x to the m term, which is exactly n plus m minus 1, choose m, which is exactly the number of ways to choose m objects from an infinite supply of n types of objects, where I can choose them with repetition, right? So this is with repetition. So this is the count. So quick example. How many 5-card poker hands could I deal from a stack of 5 or more decks? The number of 5-card poker hands I could deal from a stack of 5 or more decks is 56. So this would be 52 plus 5 minus 1, so 56. Choose 5, which is 3,819,816. Okay. Here's another example. Lay all 52 cards of a deck on a table. And we'll say face up. Take 5 identical poker chips and place some number of them on some number of cards. until all chips are placed. So, for instance, you can put multiple chips on a single card. How many possible configurations are there in this way? So how many? So I want you to think about this for a second. You've got all 52 cards of a standard deck. You've laid them face up on a table. You have 5 identical poker chips. You are allowed to place those chips on any of the cards, no matter if they already have chips on them or not, right? So if they start out with no chips on them, you have 5 chips. You place those 5 chips one at a time by selecting a card. You're allowed to repeat cards. You could put all 5 chips on the ace of spades. You could put 4 chips on the ace of spades and 1 on the 2 of clubs, right? And so on in that fashion. The question is, how many possible configurations are there? Should I lead you to it, or should I say the answer is 56, choose 5, which of course is the number we just saw. Why does this make sense? Because the act of placing the poker chips you could think of as a method for selecting a 5-card poker hand from an inexhaustible printing of all the cards. How so? If you put all 5 poker chips on the ace of spades, that would denote a poker hand, a 5-card poker hand where you were dealt 5 ace of spades, right? So every card in your hand is the ace of spades. So you have 5 copies of the ace of spades. If you put 4 poker chips on the ace of spades and 1 on the 2 of clubs, that would be a poker hand where you got 4 ace of spades and 1 2 of clubs, right? So in this way, we can see that the counts are actually the same. Okay, so this was a problem already solved. This is 56, choose 5. In fact, the way to do this is, so in general, the number of ways to place m identical objects into n distinguishable bins is the same as the number of ways to select m objects from a set of n objects with repetition allowed. And both, and thus both are equal to n plus m minus 1, choose m. Okay. One more question to prime you up for tomorrow. You can do this in any local currency you want. You could ask the similar question, but we'll use US dollars here. Quick, before I go on, I got a question. Quite confused on how to use generating function to find the number of k elements in a subset. Oh, so you are you are going back to that bit. So this was um, the original application. So the idea is building, you're doing a process for selecting the k elements in a subset. You are writing down x to the 0 if you didn't select the element, and x to the first if you did select the element. You can either select or not select an element when you're building a subset of a set, right? So if your set has n elements, you go down the list of n elements and you either pick it or you don't, right? So this is a binary thing. You pick it or you don't. X to the 0 if you don't pick it, x to the first if you do pick it. That is the binomial 1 plus x, right? So 1 plus x is the choice being made, the 0 or the 1, for each element in the n element set. Because there are n elements here, and this is done in sequence, this process happens in a sequential way. We said that this multiplication is our and. This is denoting a sequential choice. This plus is our or. It's where we have a selection. We can either exclude it or include it, right? So this would be 1 plus x is the binomial that says whether a particular element gets selected. Seeing the entire full range of all the k element subsets, I would do this n times since there are n elements, which results in this term that shows up in the binomial theorem, of course, this 1 plus x to the n. Of course, just to see this, if you have a set of 3 elements, then building a k element subset, what are all of the possible subsets, right? Well, I can exclude everything, right? That's this term. That's excluding everything. There's only one way to do that. That's the empty set as a subset of your set of 3 elements. I could include everything. That's this term. But every other term is going to be a mixture. Again, there's going to be one way of doing that. That's including the whole set of 3 elements. And then these mixed terms are including some and excluding others, right? And like which things do that here are counted by these coefficients. So this is the number of ways you have included a single element in a subset. This is the number of ways you've included 2 elements in a subset. Anyway, extra credit opportunities. I mean, it's going to be there's a lot of homework. There's a lot of homework assigned. I'm going to assign another homework tonight. Just doing all of the homework. If we'll see as I get closer. For if you have concerns, specifically about your grade, you can email me, and we can talk about it. We can see. Whether you have reason to be concerned or not. I think it'll be fine if you if you keep at the homework. Now you've basically seen the full range of what the course offers in terms of everything that shows up next is going to be a homework or an exam, and you have examples of all those things. But yeah, one more example before stopping lecture for today. So this is changing money. Just a quick question. How many ways can I make change for $1? And of course, this is, using pennies, nickels, dimes, quarters, 50-cent pieces, dollar coins, which do still exist. Okay, so we have multiple different denominations of making change for $1. The answer we'll see next time. But this is likewise going to fall to, why did I write general here? This is going to fall to generating functions. So this is just another application of generating function use. So I will post your next homework today, a little bit later today, and it'll be due on Friday, so that you can get a little bit more practice with some of the stuff since your last homework, which was just due yesterday. So look for that. I'll post an announcement when I do. But anyway, I think that is all for today. We'll start here tomorrow, so I will see you all then.